the concepts of LLM and how it functions. In the next talk by Dr. Karthika and Shruti, we will delve on how to utilize LLMs to build practical applications addressing real-world challenges. I will call on Dr. Karthika and Shruti on stage. A brief about our speakers. Dr. Karthika Vijayan works in the field of conversational AI with voice and text data, creating data science and IA solutions for real-world business problems. She has obtained her PhD in speech processing from Department of Electronics Engineering, IIT Hyderabad. And Shruti Dhavalikar has actively contributed to research projects and stays at the forefront of advancements in multifacets of AI. She has a deep passion for data science and thrives on designing models that build valuable business insights from data. Over to the speaker. Thank you.
Hello everyone, good morning. Am I audible? Thank you. So, just a little pretext. I would like to thank Professor Moninder to explain everything what is going on inside the black box of a large language model. And also thank you for setting the bar high today and making it difficult for the rest of us. But hey, I can do nothing but try, so I'm going to do that. Large language models, right? So we have established the fact that they are powerful pre-trained models. So there is no argument against it. We have come a long way from rule-based and stochastic language models, which are based on basic probability theory, to the current day large language models. The surety with which the current day large language model predicts the next word is not a random sample. They use very sophisticated use of probability theory to do that and generate very long, sensible text, one word at a time. And they are literally large in the sense that the size of the model, the number of parameters, weights, biases, everything that goes inside, and also on the aspect of the amount of data, the humongous amount of data that it is trained on. It has seen billions of words, billions of tokens and millions of words. And when you port it to a multilingual setting, it is even crazier. So it knows things. It knows things from the data that it has already seen. Now it is a bigger question, right? Does it work like magic? Wingardium Leviosa, and will it fly? So the bigger question, do they always work? So there are, of course, no perfect system that exists in this real world. So we have to address some of the limitations of this amazing model. So you might have seen news articles like this, right? ChatGPT misdiagnosing medical domain cases. It is not greatly, awesomely predicting things in legal domain, etc. What could be the reason for that? It doesn't know everything, right? It only knows developers develop real world applications using large language models. You may have seen this screenshot already. So a Chevrolet chatbot, which was powered by ChatGPT at the time, helping its users write Python codes, which is, you know, it's kindly, slightly out of scope, if you ask me. And many a times when you put such a system on production, it need not be doing that, and in many cases it should not be doing this. So that's the point. So out of scope responses. And the second screenshot is an example of inappropriate responses. Do you want your system to, if somebody asks the system to, can you categorize US citizens by race on their IQ? So it's not that desirable. So there is a little bit problem with that, inappropriate toxic responses, right? The next problem, I think all of you have heard, hallucinations, right? So this screen shows some snippets of a conversation I was having with ChatGPT. I asked it about this amazing actress, Sonali Kulkarni. I love her. And I asked her like multiple questions about her. And it did give like really sensible answers, accurate answers. After a point of time, it started making up things, okay? So the text that is highlighted in these orange boxes over here, they are all not true. It's not about Sonali Kulkarni at all. So what happened here is under-representation of data. So what these large language models is pre-trained on, the articles about Sonali Kulkarni were only a few. And then when I asked the questions, of course it grabbed the knowledge and gave some sensible answers. When I probed more, what it did was, it actually grabbed other underrepresented data, which is remotely looking similar to what Sonali Kulkarni's data was, and started making up answers. This is classic example of hallucination. Another problem, not a problem, limitation with large language model is reversal curse. It's called reversal curse. So we as human beings, if I ask you, if I tell you A is equal to B, you would obviously know B is equal to A. It's very obvious. But it is not obvious for large language models, because inference theory says we can infer something by deduction, induction, and abduction. In fact, ChatGPT, and which is powered by a large language model, and in general, large language models can't do any of this. It actually predicts the next word. And it does deductions to a certain extent, but induction and abduction out of their scope right now. So these are all the current limitations. There are a few more, like security. I'm not going to talk about those. So now what can we do, right? We do have this amazing model that is that knows that trained on trillions of data, and then trillions of tokens of data, and we don't know how to use it. That's not an ideal scenario. So let's see how to use it. So I said there is a problem with lack of knowledge. There are certain things that it doesn't know. What to do? Provide it with the knowledge. Train it, or like give that access to that information. It hallucinates and sometimes gives out of scope and inappropriate responses because it doesn't have the context, what is going on around it. Provide it with the context so that it will start behaving in the way we want it to be. And it is poorly doing on deductions and abductions. Give it enriched knowledge representations so that A is equal to B and B is equal to A is evident in that knowledge representation, and then grabbing that knowledge and responding will be a trivial task for large language models. So based on these ideas, we kind of bucketed our strategies on how to use large language models into 3 buckets, and we will dive deeper into each of those going forward. So strategy number 1 is just don't do anything with the large language model. Keep it as a black box and try to play around with it, okay? Around with the components. What is happening around that large language model ka black box, play with it, control it, and try to make the disadvantages or limitations disappear. So I'm going to present 3 ways in which you can do it in strategy number 1, just using the pre-trained large language models. One is direct querying. It is like simple as obvious as it is. Just ask your questions to pre-trained models. And it is simple and fast. There is no cost or time investment. Just take it and use it. Now what the problem with that is, we already have seen all those limitations. Still stands. None of them are cleared. But find a use case where this can be plugged in. It could be plugged in for a very generic use case. For example, a student looking help for writing an assignment. No critical consequences gonna come out of it. I mean, if he or she fails, then that's a different issue. But otherwise, ask generic questions to it. It can be a very generic personal assistant, and anything that a search of internet can do, it can also do. So we can use it for a very generic application, but the limitations still stand. Now how to address those limitations? It will only answer the very specific questions, and if I ask a very factual question, it will give you factual answer. There is no hallucination, no confusion around it. And the information has to be present on the internet. Now, how to cover up these limitations that I was talking about, right? Give it instructions. So we already said hallucination, inappropriate responses, out of scope responses happens when it doesn't have full context of what it is doing. So give it instructions, very clear instructions. If we mess up the instructions, what will happen? It probably knows the answer, but you messed up. It didn't, okay? So give it very precise, unambiguous, detailed, but not wandering off specific type of instructions. Give it the context on what it is supposed to do. for example, the Chevrolet chatbot example that we have seen, tell it you act as a customer care assistant for Chevrolet and do not answer any other questions other than the car sales and services of Chevrolet. Then I asked it, can you write a Python script? It said, sorry, I am supposed to be a Chevrolet customer care assistant. So precisely tell it what to do. And also tell it how to behave, how to act. So if this is a customer care assistant that I'm building for a ABCD corporation, I'll tell it when a user comes and says hi, greet politely. Hello, welcome to ABCD Corporation, thank you for showing interest. Then if a user asks a question about product X, Y, or Z, give it appropriate answer in, let's say, 3 bullets or 5 bullets, specific answers. Then if that person is showing interest, the customer, ask him a follow-up question. Do you want to register for, can I take your details for registering your interest? And if the customer is providing a feedback, politely thank him. If it is a good feedback, thank him or her. And if it is a bad feedback, apologize for their bad experience with the ABCD Corporation. So exactly tell a dialogue flow and how to guide the user through prompting. Now, is prompting a one-time task? The answer would be it's a big no, by the way. You have to experiment with it, chat with the system, and find the edge cases, and keep correcting, coming back and correct your prompt, keep correcting, adding the edge cases into your prompt, and this is an iterative experiment exercise. And also, it is not a one-time task in the sense that we should not give it the prompt once and then sit back and relax. We have to probably do it multiple times in order to maintain the context. So it's setting the context is as important as maintaining the context. And sometimes we can actually do it in an adaptive fashion also, train a system to generate prompts by giving all the scenarios that happens around it. And also give examples. So one example is the dialogue flow. Now what happened? We did set the context, and probably by setting the context clearly, it is able to, we are able to curb down the hallucinations a little bit, control its responses to a fair bit, and probably completely get rid of inappropriate responses for the specific use case in our hand. But it still do not have access to custom knowledge. So it cannot answer what it doesn't know. So the third strategy is give it access to the custom knowledge. Obvious, right? So it is like you make your LLM consume a custom knowledge which is important or pertaining to a specific information and use case at hand. It is like adding a memory to LLM, asking LLM, go look it up and answer the questions. So to a fair bit, we will be able to fix biases which is already pre-existing in its trained data, pre-trained data, and curb down the hallucination further. So this is an iterative experiment. Again, prompting you have to do. On top of prompting, give it access to custom knowledge. How do we do that? Now, the implementation of that. RAG. I'm quite sure we all have heard about RAG, right? Retrieval, augmented generation. 3 things, right? Retrieve, augment, and generate. What it does is, take the custom knowledge base for a specific application. So if we are building a chatbot for a specific corporation, ABCD corporation, that corporation will have all the data, right? It's sitting in their databases. Take the data, cut it into small text chunks, and then pass it to an embedding extractor. Embedding, professor has already explained, right? Embedding is nothing but a map from text to math representation, because math is all what models can consume. So convert it into a vector, every text chunk into one vector, and drop all these vectors in a database. And a new query comes. A user came and asked query about, hey, can I know about product X of this ABCD corporation? Convert that also into corresponding embedding and match it with the earlier prepared embedding and dumped ones in the database. Pick the top n ones which are similar to the query, which is called retrieved context. Now that is retrieval. And then you augment the retrieved context with the prompt, which we have to sit and write anyway, and with the query, and pass all these things to LLM to generate, retrieve, augment, generate. Little bit into detail. Why do we do text chunking, first of all? Obvious answer is LLMs cannot look up a whole database. So it is always important to cut that into semantically meaningful chunks for the LLMs to consume. And today's LLMs, most of them have a maximum token limit at the input. It says that this is all what I can look it up at once. So give it piece by piece, okay? Then effectiveness of embedding. If you take one whole textbook and generate one embedding out of it, do you think it will represent anything? No. So we have to cut the whole database into text chunks so that the embeddings are a efficient, faithful representation of the text that we are talking about. That's why we do text chunking. It can be done in multiple ways, fixed size. Every 250 character, I am making it into a text chunk. Will it work? No. You will be cutting a sentence in the middle. And that semantic meaningfulness is gone. So it's not the greatest strategy in the world, but hey, it works in some cases. Then variable size chunking is the chunking, if you ask me, personal opinion. So we can actually use punctuation mark. So I will say full stops is all what I do. Then minimum chunk size I'll get is a sentence. And sentence is a semantically meaningful chunk in itself. So I can do sentence embedding and maybe sometimes look at other punctuations also and cut it into phrases or whatever. So punctuations is a great way to do chunking. And we can extract one embedding out of each chunk. Recursive chunking, again, right? Ask a machine to do it. So basically, you will train a machine to cut big database into small 2 pieces, then 2 into 4, then 4 into 8 to a finer level when you are satisfied. So it's like a bottom down approach, cutting recursively. And customized is an interesting thing, and it will only will be applicable only in few cases where you already chunk the data set using one of these strategies and pass it, tag it with a meta information. So if it is a ABCD corporation's data set, you can say text chunks 1 to 100 is about product X. 101 to 200 is about product Y, okay? Which means if a user queries about product X, just look into chunks from 1 to 100. And you don't have to look at elsewhere. So that is like a making it faster approach. So that's the customized chunks. Then now these chunks are ready, we have to extract embeddings. Embeddings is just the math vector representation of the text. And I think professor has already covered what it is, and earlier there are embedding models available. Earlier strategies like word2vec, BERT, etc. Give you something like a BERT gives you 768 dimensional embedding. Word2vec gives you 300 dimensional embedding from Spacey. These are all packages. And current day LLM itself will give you the embedding, okay? LLMs, OpenAI's ADA LLM gives you 1536 dimensional embedding, and their previous model, this smaller model is ADA, by the way. The smaller model is called, the bigger model is called DaVinci, and DaVinci will give 12,288 dimensional embedding. So the embeddings becomes larger, and you can choose which one do you want to use depending upon how much memory you are, what kind of processing you are looking at, etc. So the embedding, effectiveness of embedding, I think we have already covered. It captures the meaning of words. It captures the meaning of the text by looking into what is happening around it, capturing the context. So if you have sports related words, it will all go into one side and sit, because they are closer in meaning, which necessarily means that they have similar embeddings, vectors. Similarly, all fruits will go to one side, vehicles will go to one side, and so on. And if somebody comes up with a new word called apple, where do you think the embedding will be? Near the fruits? What if I tell you I'm talking about Mac? Okay, so context. That apple will have a different context. Courtesy Louis Serrano, that was his example. I'm borrowing from him. So we now have text mapped into vectors, and the vectors are efficient representation of text chunks. And when a new query comes, just have to do a vector similarity search. Now it is not just vector similarity search, right? Because the vectors itself captures the meaning of the words, it necessarily becomes semantic search, because the semantics are inherently captured inside the vectors. Then a rough similarity search will give you semantic search. So you do semantic search, pick the n most similar vectors, grep the corresponding text chunks. Those are the retrieved context, right? Those are retrieved context. Now augment, we already covered that. So take the retrieved context, which is basically the custom knowledge, write your own prompts in whatever way we discussed earlier, concat with the query itself, the user's query. 3 of these things you augment, pass it to the LLM, and now we can completely rely on LLM's text generation capability, language generation capability to come up with precise, cohesive answers tailored to the query. Okay, so we started with a couple of limitations. I guess we have addressed hallucinations, provided with context. Hallucinations can also be a result of lack of knowledge, so give it custom knowledge. Lack of knowledge, hallucinations, inappropriate out-of-scope responses, all these things can be curbed down or reduced to a fair bit by this strategy number 1, which is just using the pre-trained model and working around it. So you can directly query it for generic use cases, prompt engineering to provide context, and on top of prompt engineering, give it access to custom data so that all these strategies will come together and enable us to build real life applications. Let's move on to strategy number 2, which is fine tuning the models. So we are going to, so in the first strategy, we did use LLM as a black box. Now in second strategy, break it open and we are going to tinker with the weights, biases, whatever is happening inside the LLM. Okay, so that's the second strategy. Now you can ask me why. We already have seen RAG, right? It did a fair good amount of job with all the limitations that we are talking about. I want to take a step back and look at RAG. What it does is you ask LLM to look into certain information. You are giving it a page and say that look it up and answer this question. You are not making it learn that information. Okay, it's just I am giving you like, oh, dev day. You may ask me, what is dev day? Here is a write-up. Just look it up and answer the question. Now, another problem with this strategy is semantic search is also like not a 100% accurate. So there are cases where you can make it worse. Probably the pre-trained LLM knows the answer and you passed it inaccurate information which contradicts with its pre-existing knowledge, then you can make it worse because of the lack of accuracy in semantic search. So RAG is of course cost effective, simple and fast to implement, but may not be the best strategy always. That's why let's train the LLM. So of course there are nuances associated with it. You have to find budget. It's an expensive business to train an LLM. So we do fine tune. We cannot train an LLM from scratch. And it requires computing power, cost, time, of course. All these limitations are there. Then why do we do it? I want to give a quick example. Imagine a high school student who has a doubt in his math class with respect to trigonometry. He went into the teacher's room and looks for the teacher. Unfortunately, the math teacher is not available. History teacher is there. So, recap, the history teacher is pre-trained in math. So, he or she has finished her math class before becoming a history teacher, right? And the student did go with the textbook and can you see, this is my doubt. So, the teacher can look it up and maybe reload pre-existing information from her classes back in the day and give the answer. Which one do you think the student will prefer? Hearing it from the math teacher or the history teacher? I think it's obvious. But then there is a problem with that. If the student has an exam like in another 10 minutes, it would be better to hear from history teacher. But if the student has to submit an assignment next week, maybe he or she can wait for the math teacher to come back. So that's the contextual difference between RAG and which one to choose. So we need, in fine tuning, we trains the LLM so that it knows that custom knowledge rather than looking it up and framing an answer. So that is fine tuning. And what are the ways in which we can do? Derive the model, that is do task specific fine tuning. Take a task, whatever the task that you want LLM to perform, prepare the data, you have to label it, oh, this means this means this. So if it is a question answer bot, you have to prepare QA pairs for the LLM to learn and train it. And once you get the trained LLM, you chat with it and see how good or bad it is doing. And then that result becomes a second level of training data for the LLM. Somebody has to mark it, this answer is good, this answer is bad, this answer is not usable, and you created a secondary training data, and if refinement is required, go back and train it again, stage 2 fine tuning. At the end of the day, what will we get is an assistant model which is derived from the pre-trained LLM, which also has the required domain knowledge or the custom knowledge that you want it to have for the specific application that you had in mind. For example, if it is medical domain, take it and use it, train it with respect to all the pediatric cases so that it will do a better job while classifying pediatric diseases going forward. Same case with legal domain. So that is one place where this is absolutely required. So I said you can choose between, right? Sometimes you cannot choose. Because if you want ChatGPT to work in pediatric cases, there is absolutely no way other than making it train, because pediatrics, medicine, they are not generic use cases. They are expert heavy. So you have to train it. RAG may not work. Same goes with legal domain, where you need a specific writing style. It's ChatGPT or LLMs do know how to write an email. Does it know how to write a third-party contract? That is a very specific writing style with specific legal jargons. So you absolutely need to train the LLM. Now, multitask learning, this is an interesting extension of fine tuning. This is basically fine tuning. You are trying to construct a dialogue system or a conversational system. There are multiple tasks to do in that system. You have to understand the intent of the user. You have to understand what the user is talking about. Hey, I would like to know about product XYZ. What does that mean? He would like to know. About what? Product XYZ. So intent recognition, entity extraction. These are two tasks that you have to do for archiving. Then if the user is providing feedback, you have to do a sentiment classification, and all these can be done from the same set of data, right? It's a conversation, a person coming and chatting with the conversational assistant. Each of those sentences can be tagged for each of these tasks and do a fine tuning in one shot. That is multitask learning. Very good when you are completely, when you are building a very complete system with has multitask to do, and it can be done from the exactly same one set of training data, ideal scenario. So that is a second strategy. Third strategy is transfer learning. Imagine I did train fine tune an LLM for a QA activity. I do want to do sentiment analysis also later at a stage. Now what will we do? Take that LLM who already knows QA of that particular domain, tag a small data for sentiments in the same data set, and do a second layer of fine tuning. So you are basically transferring the knowledge it captured during the QA task, training task, to do the sentiment classification also. So that is the third strategy. So I would like to summarize. In the second strategy of derived models, deriving a model from pre-trained LLM, what do we have to do is fine tune for a specific task, or fine tune for multiple tasks at once, or use a trained model which is trained for a specific task and use it for a different task later. Now let's quickly deep dive into how it has to be done, right? So I'll pass the stage to my co-speaker, Shruti.
Hey, as you can clearly see, I am the kid in the speakers and got this sweet spot speaking after Karthika before lunch, so bear with me for a while. So fine tuning, we'll go ahead with fine tuning and understand what fine tuning does. So as Karthika said, LLMs are black box. Let's actually open that black box and deal with weights and parameters and how the fine tuning is done. So see this figure. What you can see over there is there's a model and there's a task, that's a classification task, and previously the data was English, but now your requirements are changed and now suddenly you want your input data to be in Spanish language. What would you do? Would you change the whole model for it? No, right? What you'll do is you'll fine tune the model for the newer data which you want to add, that's Spanish data. And after fine tuning, if you give input in your required data format, that's Spanish now, then the model gives you the prediction. That's definitely what we are trying to do with fine tuning. It's a task specific fine tuning where there's a defined task, and what you need to have with you is you need to have data and you need to have compute to do the fine tuning. Now let's take an example to understand transfer learning, fine-tuning a little bit more, and then we'll see about the other perspective, that is data and the compute. So let's take this example. Back then when ImageNet was released, CNNs used to get pre-trained on ImageNet data. Just to summarize ImageNet a little bit for everyone, ImageNet is a huge set of image data where there are 1,000 classes, and for each class there is around 1,300 examples for ImageNet. Now, when you train your CNN for ImageNet data, it predicts output from those 1,000 classes. If you want to use the same CNN to predict or detect leukemia, then what would you do? Now your input images are changed. Your input images are blood smears. Blood smears, by the way, you put like a drop of blood on a glass side, and then you slide that up, and that's like a blood smear. That's like a micro image of that. Now, you have a model, that's like the base model, that's CNN, and then you have your newer set of images. What you do is actually you import those weights or parameters, and you give new data to the same model, and now you ask that model to predict whether the leukemia is present or not present. That's the fine-tuning. So all what you need to do fine-tuning is to have a base model. Now, let's come back to our own domain. That's the LLM use case. If we want to train or fine-tune any LLM, large language model, then what can we do? What is our base model? Our base model is the LLM itself, right? Because it is trained on a humongous amount of data, as Karthika said. So we have a base model. Do we have data available? Now, if you want to use LLMs for a particular use case, for a particular business, then they'll definitely have some enterprise data available with them. Of course, we need to clean the data and we need to label the data, as Karthika said, but that's still doable. And that's still, that is something that we can still afford, we can do. Now let's talk about the third, that is the compute. Do we have compute available to fine-tune these sort of models? Before saying yes, let's just take a look at the numbers and then say whether we are able to say yes or not. So, just to tell, LLMs are huge. How huge? Let's take a look at this image. This is, by the way, if we want to train our LLM, then let's take one example of open source LLM. Now, Llama 2 is like the LLM released by Meta. And these are the versions. In the column 1, you can see if that's visible from backside. So I'll read it out for you guys. So it's 7, 13, 32.5, and 70, like 65.2. So those are the types of Llama 2, or rather, it's the same model, but then the number of parameters. And those parameters, trust me, it is in billions. Okay? So, and the second column that actually suggests that if you want to load this model in your memory, then it is going to take this much of GB of data. So, any one of you who is carrying computer, do we have this much of RAM available in our computer? No, right? So we cannot say that this much of compute is readily available with us. Maybe with a stretch, with the online cloud computing we can, but still, there's like a little bit of hunch there, a common trade-off. If you want to have good results, if you want to have good accuracy, then you need to use a model that's big enough to understand the context. For example, the ChatGPT 3.5 Turbo, which we usually use, it has 175 billion parameters. We were just talking about 7 billion parameters and 28 GB of RAM. So that's the range we are talking about. So if that's the case, if we need to increase our model size to attain a good amount of accuracy, and also we need to have huge amount of data to train our model to make it understand what you are trying to make it understand. So if you increase these two parameters, then definitely your accuracy is going to increase, but at the cost of you're going to have increased compute for it. Same goes, if your model is small, if your data is small, then of course compute will be small, but then the accuracies will be bad enough. So do we have any solution for this? Can we accommodate compute somewhere so that we can have like a fine-tuned model with a better accuracy? The answer is yes. Like there are multiple acronyms over here. I'll explain the second one first. That's PEFT, which is parameter efficient fine-tuning. So let me explain first the parameter factor of it. What is parameters? Parameters are usually called as weights. People also call it parameters. Parameters or weights, they are actually just the numbers when we download these llama files, llama 2 files, then what we download are these numbers, but within those numbers, there's knowledge hidden somewhere. These numbers are interlinked in some non-linear linear functions, which will actually contribute to the actual knowledge of that large language model, the understanding of that large language model. So those are parameter. And if you want to do parameter efficient fine tuning, then what you can do is this. This is LoRa, which is low rank adaptation. What it actually does is, there's a concept called as adapters. Let me go a little bit technical here, just to summarize. You have some pre-trained weights. Pre-trained weights as in the normal weights which we download. You can have like a similar metric, but then out of all those weights, you can only take out some particular weights and train your model so that you are saving on compute, right? You are not training the whole weights altogether. And what is those sum weights? Those sum weights are characterized by R, which is actually the rank. So in mathematical terms, if your weights is just metric, which is m cross m, then you are going to take R cross R out of that metric, which is like the R hyperparameter over here. So out of m, only small portion of weights you are going to train, but then that is going to give you the equal amount of accuracy what we'll achieve after training the whole set. So that's good, right? We are saving on some compute, and it's totally dependent on R. So just to tell, if you decrease R, then it is going to, of course, hamper your accuracy, but you can optimize your R so that you can have good accuracy and also you can optimize over compute. That's why I called R, which is actually rank, as a hyperparameter. Okay, and that's actually low rank adaptation. Now, what if you further want to optimize on compute? That's not good enough. Itna budget hai nahi, aur chahiye saving. So then what is it that you are going to do? You're going to you're going to quantize the model. Just to explain what is quantization, quantization is, for example, if you have a number called as 2.00007. Now it's as equal as 2, but then that 00007 is going to take like a good amount of memory to store in the memory, right? So you can just cut down on that 00007 wala part, preserving the true meaning of 2. That's like the underneath layer of quantization. So rounding off, truncation, all these examples of quantization only. So if you can do quantization just to load the model in your memory, then it will require less amount of memory. If you remember the figure which I showed previously, then it was having float 32 format of llama, and then later the columns were increasing. It was having int 4 format, which is like a decrease, quantized format, and it was taking much less of a memory, which is like 4 GB or whatever. Now, I am sure every one of you have 4 GB of RAM on your computer, right? That's something we all can afford. So that's what the power of quantization or QLoRa is. The quantization will allow you to load your model in the memory, and then what after quantization? You perform LoRa, right? The same example. Just the thing is, a bit technical aspect of it, when you load your model in your CPU, that's like in the quantized format. But when you actually perform the forward pass and the backward pass, that is the updation of the weight, you actually convert the model back again into 32-bit format or whatever was the original bit format. But in that way, you are not actually expanding the whole model, but then you are actually partially expanding it. So that allows you to enable a little bit or save a little bit of compute. So that's the power of QLoRa, and that's how QLoRa operates. Now, since we have introduced one more parameter, we must check, right, with respect to that factor, how our accuracy and compute going to be. So as we saw, model and data increase, accuracy and compute going to increase. But if you decrease quantization, what I mean by decreasing quantization is, for example, originally it was present in 32-bit format, all the weights. If you decrease it, if you quantize it to 16-bit, then that's one. If you further quantize it to 4-bit or 2-bit, then that's more the quantization. So if your quantization is less, if your bits are more, then your accuracy is better. But then if your quantization is more, for example, from 16 also you are getting it to 4 or 2, then your quantization is increasing, but then it is going to decrease your accuracy. But it is going to decrease your compute too. So all these things, we have to tweak it in such a way that that's the most suitable for our use case. So that's like the relation between these quantities. So let's summarize a little bit what I said so far. One is, we talked about fine tuning. What we do in fine tuning is we need to have clean data to feed to the model. We need to have resources to train our model on. And we have checked accuracy trade-offs, how that trade-off becomes with respect to with respect to model size and with respect to data. Then we talked about LoRa. LoRa is actually low rank adaptation, where R is your hyperparameter and it helped you to reduce your resources. Second is QLoRa, where quantization parameter was there, and with respect to quantization, how our accuracy and compute is going to differ. That's about fine tuning of LLMs. Now, let me give you the additional example. For example, you are asking a person to sell something, giving a pamphlet, like this is the pamphlet, this is the product, now you have to sell that product to the audience. That person will be able to do that, but not to a very good extent, right? Now, assume that you're going to take that person and give the internship to that person in the same company. Now that person is going to work with that company for maybe 6 months, and after that, if you ask that person giving the same booklet and to sell the same product, then do you think there will be a difference? There will be, right? Why there will be a difference? Because now the person knows the lingo of that business, the features of the product, what are the upcoming features also, something about the business, something about the domain, right? That's always helpful. So that's what fine tuning brings. But what you want book also, right? You cannot always let that person go on himself or herself, right? So that's like the hybrid model, which brings you best of the both worlds. You're giving the pamphlet also, and you're giving the internships also, so that finally the person knows about the domain also, and knows that's there in the book also, so that the person can sell the product very efficiently. And that's the RAG plus fine tuning. How we can actually do it, if we want to do it for a particular business, is we can actually implement a RAG, retrieval augmented system, and then fine tune the model on the similar domain data or the enterprise data, and then use that LLM, the fine-tuned LLM, to generate a response in the RAG or retriever augmented system. In this way, your model already knows about the domain also, and it is able to access the external data through RAG system also. So it's like best of the both worlds. Here, you can see there's like a direct comparison. What are the things that RAG is able to provide you, which fine-tuning is not? What are the things that fine-tuning give you, which RAG is not able to do it? But then, if you combine both of them, then you are getting best of the both worlds. And that's what we already want, right? So everything is sorted, right? Karthika has mentioned so many problems. We have sorted with the compute also, and now we have everything. Shall we go for lunch? That's good enough, right? So we address this problem. We address this also. We have control over the responses by prompt. Lack of domain knowledge, of course, we are letting the model access external data through lag, so that's also addressed. Hallucinations, that's sorted because we are using RAG. Oops, there's one thing that we forgot. This is the reversal curse. Do we even know why we are not able to address this problem very properly? Let's first understand what is the problem. And to solve this problem, we need to enrich our model in one way. Let me give you one example. So for example, when we were using RAG system, RAG system, our external data, that's like the access to the external data, it was stored in the form of text and text embeddings. That's right? We all said yes to that, text and text embeddings. So what is it that the text embeddings is not able to give? Why the LLM was not able to give you answer that mother of Tom Cruise is XYZ, but the son of XYZ is, I don't know, Tom Cruise, why it didn't so? That's because of this. Aid LLMs in deduction. For example, we also, even in professor's lecture, even Karthika said it multiple times that LLMs are good at prediction, but they are not good at deductions, because those are two different tasks, right? We cannot expect one LLM to do everything. So we should help LLM to do these deductions. But then we can clearly see our text embeddings or text data is not able to give you these deductions directly. Correct? So can we think of something, some external data set, some external storage that can allow you to store this bidirectional this relationship, and which is also structured in format so that we can query that. So can we think of something? I can readily give you the answer because my talk is based on that. So this is knowledge graph. Knowledge graphs gives you this relationship preservation. And can we integrate this knowledge graph with LLMs? Definitely we can. So this gives you best of every world. You can store your information very efficiently in a knowledge graph, and then you can use LLM to formulate a response on top of it, so that your response, which is grounded by a knowledge graph, which is your own knowledge graph, and then you'll have like a certain response, which covering all those limitations which we saw previously. Everything is good to talk. Let's dive into how we can do it, right? So it is called as graph augmented generation. Previously we saw retrieval augmented, where we were doing text retrieval. Here we are going to augment the graph information. So let's see how we can do it. Let's go slow a little bit and then jump from the steps 1 to step 5. First is to give this information. For example, somebody asks question like, who is mother of Tom Cruise? Okay, answer is done. But then if answer is XYZ, then who is son of XYZ? Then you have to actually retrieve that information from the knowledge graph, right? So what do you do to retrieve information from a knowledge graph? You query the knowledge graph, right? And since all of us, trust me, all of us, we are developers and we have used multiple LLMs to write codes for us, correct? So we know that ChatGPT or any other LLM, in fact, is good at programming languages plus the other spoken languages also. So it's language agnostic. So if you ask a graph to query, if you ask the LLM to query the graph, then definitely it will be able to query the graph. If not, we have the solution, fine-tune your model, it will be able to do it. Definitely, right? So our LLM is going to query the graph. It will be a semantic search only, as Karthika said. It will be meaning underneath which we will be capturing. So it will be semantic search over the graph now, not on the vector store, by querying, by generating the ciphers. Then, the embeddings which we are going to get at the end are the graph embeddings. Now let me tell you a difference of text embeddings and graph embeddings. Of course, both of them, they carry the semantic meaning with them for the given text, but then graph embeddings on the top carry the original topology of the knowledge graph with it. For example, if I am friends with Karthika, Karthika is friend with Karun, then of course that embedding will know that I am friend with Karun. In the text, you have to explicitly say that I am friends with Karun also. But in graph, since this topology is maintained, of course, it will have that underneath meaning captured in the graph embeddings. So our graph embeddings are much richer than text embeddings. And now we can leverage those graph embeddings. What we do after getting embeddings? The same thing. Augment it with prompt, augment it with query which is asked, and then after augmenting, generate a response. And that's how you will get LLM respond to your query grounded by a knowledge graph. But then, what is the best advantage of it? One is you have your own knowledge graph to feed to the LLM so that you will have some basis of what that LLM is answering. And second is, the LLM is going to give you a beautiful response. All of us, we love it, right? What any other large language model says. Now, the bigger question over here, if somebody has spotted, is we need to have a knowledge graph at first place, right? That's the bigger question. Now, how can we do that? The same LLM is going to come to rescue us for that also. LLMs can be used to create a knowledge graph also. How can we do that? The same thing. What Professor said, what Karthika said, right? LLMs can do the task of entity recognition, the text extraction, the extracting information from the given text, or information extraction. Everything can be done using LLMs. Why? Because they know languages. Since they know languages, they can perform all these tasks. Now, given a document which is like unstructured data, can you collect information from that document and put it into a tabular format? For example, if a document says about product specification, their compute, what and what not, can you capture that sort of information if you train LLM to do that? Definitely it can. Can you convert then the textual document which is unstructured into a structured format? Definitely you can. And if you have structured format, can you construct a knowledge graph out of it? Definitely you can, right? So that's how we create graph embeddings, and that's how we create knowledge graph. So all of it, it becomes a collaborative system. You use LLM to create knowledge graph, and then your knowledge graph is going to give information to the LLM to construct the answer. Isn't it like a good ecosystem to be in? So that's about it. So we saw LLMs are really powerful models, as both of my co-speakers said. LLMs are really powerful, but they have some limitations. Throughout the talk, we studied the strategies, how to address those limitations one by one, and then appropriateness of these strategies. For example, where RAG can be used, where fine-tuning can be used, can we use both of them, what and what not. And we also use, if we have these individual systems, then can we use all of this, for example, RAG, fine-tuning, graph, everything in combination so that they can give birth to a hybrid ecosystem that can actually serve the purpose for any business. So that's about our talk. If you have any questions, please reach out to us, me and Karthika, and we are happy to answer your questions.
Thanks, Karthika and Shruti, for presenting strategies for using LLM in practical applications. If we have questions, we can take questions now. The other way is you can add the discussion points in these sticky notes that's on your table and stick it on the glass wall that's over there. We can take all these questions in the end of the session, the last session, that is birds of feather. But if we have any questions specific for our speakers, we can go ahead now. Yeah.
What are the properties that you're trying to capture in such a graph knowledge?
So there is no one answer to that. First of all, we have to define what the domain is and what is the knowledge graph supposed to capture. So every knowledge graph is associated with an ontology, you probably know, and the ontology is many a times motivated from the domain and the application. For example, if I am using that pediatrics example, right? So there is going to be diseases, diagnostic terminologies that are associated with diseases, the treatment, and then diagnostic tools. So these are all different type of entities that I can capture from that particular domain. Now, can you capture the same entities from legal domain? No. So the ontology, the definition itself is different. The entities that we are capturing are different. So we have to define that first. Once we define that, that becomes our entity definition. Relationship definition. What mother and son cannot be the relationship between pediatric diagnostics and diagnostic tools. So the relationship is different. So all these things we have to define ahead of time. Using our domain knowledge, I am not a medical expert, so I have to ask a doctor to come in and define this for me. Once we define it, it concisely define my ontology definition. And then I can train an LLM if it already knows, if it already do not know, or use the LLM to capture this information. And then there are graph databases where you can put this information into a schematic. So, you know, Neo4j and whatnot. And then there are Cypher queries or SQL queries, not SQL queries, SQL queries is for other data, Cypher queries that you can write to query the LLM, retrieve the context, give it back to the LLM to generate the answer, then the whole picture will be clear. Did that understand?
Just a follow-up question. So does that mean that this is for like a specific use case, like medicine, law? Like how does this apply for a generic use case?
So generic use case.
Sorry, the question was, are these graph instructions very specific to a specific domain use case like health and law, where they have certain these kind of explicit relationships, right? So is this applicable for a generic use case like what we see in chatbots nowadays?
So we can generalize it as much as we can. That's my answer. So if you look at entity definitions, any model, not LLM, any language model gives you 17 different entities. Spacey gives you 17 different entities, and it's like 2 plus 2 minus. So what are the entities? Name. Name is always going to be there, like people are there. Place, organization, country, geographical entity. So these are all general purpose entities. Now with respect to these general purpose entities, we can come up with some ontology, and Google Knowledge Graph has a huge ontology. So the generalization is not like pure sense generalization. I mean, that is even doesn't exist in the real world, right? So the answer is, hey, we can do as much as we can in a generic context, and it can actually, we can even that generic context we can use as an enrichment, but don't bank on that completely. And find out generalization strategies from everywhere for generic usages, but that anyway our LLM is doing. So this is mostly for specific cases where the generic LLM is going wrong.
And just one more point over there. So if you want to make it as generic as possible, then you'll require that amount of data also, and that to tag data for it. So then that's like, again, a huge task for it, right? So then if you want to make it specific, then that's a smaller task and doable task.
Any more questions?
Thank you for the talk. It was very informative. I was looking at it more from finding out how to use these. Right? You talked a lot about how you can train it and control what it is. Say I have an LLM. I have it tasked to a specific objective. Say for example GitHub Copilot. Right? It's to specifically help developers. And then you have a knowledge graph which narrows it down to say that okay, do what you're supposed to answer it this way or not answer it this way in general terms. If I'm a user of this, would I be able to discover what the boundaries are of what I'm doing? Say for example, I'm using GitHub Copilot, maybe wrong example here, but I'm using it to generate automatic scripts for deploying infrastructure. But I want to make sure that any script that it generates does not give elastic properties to the container, because it might end up creating something which I will have a massive bill for tomorrow, right? So there's a logical limitation that I want to place on whatever it's generating. Now I don't know if that has been, I don't have the time or energy or even the knowledge to be able to create a knowledge graph to specify that. But can I discover what the limitations are of whatever has been trained on? I hope my question is.
Yes and no. So we can do that to a certain extent, because knowledge graphs are widely used for analysis, discovering relationships, etc. Drug discovery is a very prominent application of knowledge graphs. For example, COVID happened. Nobody knew about COVID before. But we knew about SARS. We knew about anthrax. And there were medicines, vaccines existing for those diseases. And a knowledge graph is what aided not aided, I would say sped up the discovery of vaccine for COVID, because analysis happened on previous things and prediction happened on the newer things. And then of course, it was not machine learning people who did that. Of course, it went and gotten verified with the doctors and whatnot. So discovery is definitely possible, but can you do that endlessly, right? So no. So certain amount of domain knowledge is required to place those rules where the limitations are. That's why I keep getting this question, will AI replace us? My answer to that is no. Because at any given point of time, there is that one person who knows the domain is required. Now we can train the LLM for every domain possible. Of course, it is writing codes, Copilot. It is answering text-based questions and whatnot. But the bounding boxes that we want to place around it, there are absolute bounding boxes that we definitely don't want it to break. For example, the example that you just shared. We can place it as a rule and make sure everything follows that rule. But there is an undiscovered rule. We will only discover it. We can do the exploratory analysis through which we will discover some risks, which is true for any other application. But then there are certain risks that we will discover on production. So, yeah.
Thank you.
I have one point to add. So now me and Shruti has actually presented very ideal scenario, rainbows and unicorns. I am looking at those folks who are standing on the backside, right? Sibin, Karthike, Karun, Ajinkya, Suman, Venkatesh. They are going to disagree with us and provide you with a whole different landscape of not rainbows and unicorns. Thank you.
Okay. Thank you, Karthika and Shruti.